Okay, so we are already recorded.
Okay.
So we are not talking about American elections anymore. We are going to proceed into mathematical part of our discussion. So today I'm glad to introduce a young mathematician from the Czech Republic, Radek Cibulka. You can see him on the screen. He is a young mathematician, but he is already pretty well known in our community, variational analysis and optimization. Now Marián has appeared. As far as I understand, Radek is a former student of Marián and keeps working with Marián. This is probably a joint paper of them. I know that Radek is involved in North America as well with ASEAN. So he works with key figures in our field. So as it was already mentioned before we started, he comes from the city called Pilsen. And up until recently, this city, in my mind, was associated mostly with the Czech beer. Now another association is Radek. So, I'm not sure when we will be able to taste Czech beer again, but at least we are hoping to see Radek at our seminar occasionally and possibly also at our workshop in December. So, Radek, I am passing to you. Please tell us about those implicit functions and all the stuff you are going to tell us, please.
Okay, thank you very much for kind words and for the invitation to give this talk. My plan is to present a joint work with Marián Fabian concerning inverse selections for nonlinear mapping, and I try to motivate the results, and I also want to present some proofs. Yeah, so I hope that everything will go fine. So the motivation is the following. Probably everyone knows the usual classical nowadays Clark inverse function theorem, which is for local Lipschitz mappings, which simply says that if all the matrices in the Clark generalized Jacobian are non-singular, then you can locally invert your non-smooth function, and this local inverse is Lipschitz continuous. So this is say statement C, yeah, so this is Clark. Then of course you can have a question: what about the non-singularity of the matrices? Then you need the same dimensions in the space, so in domain, in also in the range. So what about the case when the spaces have a different dimension? Then of course the target space has the dimension less than the domain space, but you have then quite similar result. Say for example P, it is due to Pursio, and it says that if you replace the non-singularity condition by the assumptions that all the matrices in the Clark generalized Jacobian have full rank, then you obtain so-called openness around the reference point, and not only openness but the dependence of the size of the balls in the domain and range are related in linear way. So you have openness around the reference point with linear rate. So if you have these two statements, C and P, then you can ask whether one can be proved via the other. So for example, if you have Pursio result, then you can prove from it the Clark's result very easily. So this is easy to prove, and of course the natural question is whether I can use Clark's theorem to prove the Pursio's result. I think that there is one interesting paper or preprint by Marián Fabian and David Bartle, who are joined also to this talk. So if you have any questions, any question concerning the possibilities, or maybe it's not possible, I don't know, to prove the Pursio results from Clark, then ask them, because I think that they are the most experts in this and they are quite involved in it. So I am not discuss this implication, but rather discuss a different issue. If you have Clark theorem, you have Lipschitz continuity of the inverse. So the natural question is, if I have Pursio result, can I select, of course I cannot invert, but can I select from the inverse mapping, which is set valued? So in general, my set value inverse mapping is set valued. Then can I select some mapping which is continuous? So this is the question which was successfully answered quite recently, and we started to look at the preprint with Marián and come with some generalization, say, in Banach space setting. So this is the aim of my talk. I will start with, so the paper is due to three authors, and again the question is if I can select from the inverse mapping nice selection such as continuous and so on. I will make it precise later. So I want to start with a statement which is the key result in the very beginning. So I probably you well familiar with Echelon's variational principle. So this principle says that you have some lower semi-continuous function, and you can find epsilon minimizers, something like this. And if you use the Echelon's variational principle in our setting, then you obtain the result which I am presenting now, which is the key proposition. And what is it about? Suppose that you want to solve the equation g of x equals y. Yeah, so this y is given. It's a given point in some set. So I have generally a set of possible right-hand side, and this y is given, and I want to find some x. So the question is whether there is a point x in another set which may represent the constraints of the problem, such that it is a solution of the nonlinear, in general, non-smooth equation. So we can have the following statement. So I have my G, which is defined on the whole set, and suppose that I am able to find two functions. First is the metric on the space X, which in generally depends on my right-hand side. Yeah? So generally, for different right-hand sides, I am able to produce different metrics, and the space X with this matrix is complete. And then I want to find also a function on the target set. Again, this function can depend on my Y and have some properties such as that is finite at some reference point, and the preimage of Y contains only, for example, 0. So then if the composition of my G and this new function on Y is lower semi-continuous and satisfies the following. So the first condition is that you are not at the solution. So if this quantity would be 0, if I had here 0, then X would be the solution. So this means simply that G of X is not equal to Y. So I have a point, and it's not a solution. And I have to be able to find a better point. Better, what does it mean? It means that if I calculate this quantity, which is here, then it is also here, and better means that I make this quantity smaller at my better point. And if I am able to do it for each x in X, then the conclusion is that there is a point such that it is a solution, and you have some distance estimate on the desired solution. So this is a key principle which gives you the solvability of nonlinear equation. And just I don't want to present the proof, yeah, but just to see how long it is. So it is, say, 10 lines at most, yeah, using Echelon's variational principle. This statement, what I'm presenting here, can be found in an old paper by Fabian and Price. Yeah? So it's quite old result, and the year we are talking about is 1987. Yeah? So it's quite long story. And what you can obtain from this proposition, then of course openness with linear rate or metric regularity if you want, and what of course more general statements, and especially the possibility that I can make everything dependent on my right-hand side. This allows to obtain from this result also regularity in Fréchet spaces. So it's quite general and quite powerful tool. So let me present two consequences of this. The first is the usual openness with linear rate around the reference point. Yeah? So I have a reference point, and the conclusion is that the image of the ball with some radius contains a ball where the radius is multiplied by a constant. So this is something like openness at the reference point with the linear rate. If you want to call it in terms of inverse, then it is so-called metric semi-regularity or hemi-regularity. So this is the statement, and again, how it works. For you give me x and y, arbitrary, and again, this condition simply means that f of x does not equal to y, and I am able to find a better point. Again, better means that this quantity is minima is something, and you make it better. Yeah, so it's smaller, strictly smaller, and you have also some multiple of the distance. So again, the conclusion is the openness with linear rate, and how to prove it? 2 lines. You simply apply the general result with this x and usual function produced by the norm, and you are done. So this is quite well known, and you can obtain from this, of course, also metric regularity around the point. What we done with Marián was the following statement, which can be more complicated, and but it's not so surprising to have such a statement. And again, you have a mapping F, you have some reference point, and you want to find the continuous selection. So just maybe I can return back a bit, because if you have this statement, this proposition, the first, the simpler one, then it in particular says that the inverse mapping has a selection which is single-valued, defined around the reference point, and is calm at this point, but says nothing about the continuity of the inverse selection. So the difference is that now the conclusion is that you can find a mapping phi, which is, this means continuous, defined on a ball around the reference point, has values in your domain, and for each y within the ball, you have this, which means that my phi is a selection of the inverse mapping and is continuous. This is the first. And the second is that it is calm. So it has one more property, namely the continuity. So the calmness and the non-emptiness on a neighborhood of the reference point is from previous proposition, but now we added the calmness and continuity. So this is just an idea of the proof. You apply the first proposition for this x, so all continuous functions phi with values in omega defined and on the whole ball around the reference point, which are satisfying 6, and then you consider the composition. So my G in the general statement will be composition of F and phi's from this space, and the target set will be again the space of continuous functions with defined on a neighborhood of the reference point and with values in a slightly bigger wall. And what about the assumptions? So going back, again, for some function, you have to be able to find a better one. So if you give me a function phi, and this condition, which is written here, so it's quite complicated written, but means nothing else that if you compose f and the given phi, then it isn't the identity. Yeah? So this condition, what I have said, is that your composition isn't identity, and you have some distance. Yeah? Again, here is the distance between f at phi of y and y itself. And again, the statement is such that you have to find a better mapping such that you have this equation, this inequality 6, and you minimize the error. So if you look at this quantity, what is on the right-hand side of the 7, the relation 7, then this measures the error between the composition and the identity. So you take supremum, which is the error, and you have to minimize this error. So your function, new function phi, has to be better with respect to this error. So this is the statement in Banach spaces, and I will show you how to apply this statement in the proofs. Yeah. So again, just to have impression how long the proof is. So say 20 lines, but you have we have written everything very, very carefully down, and I think that the application is straightforward. So now I want to present as a motivation the Graves theorem. Everyone probably knows the Graves theorem, and what is it? So you have Banach spaces, you have a nonlinear mapping, and you have some approximation by one linear mapping, and my approximation is open. So the first condition is that the image of the ball contains sufficiently large image of the ball in the target space. So again, you have some linear dependence here, and the second assumption is that your approximation is good, say strict. If you have strictly differentiable mapping, then this mu can be made arbitrarily small. So now I have some error in the approximation, and my approximation has to be sufficiently open, so my mu is also here. And the statement is the following, that for each constant c, for which is strictly less than alpha, for each reference point and for each radius within this interval, the following statements hold true. So the first one is the usual Graves theorem, which means that for each right-hand side y, you are able to find a solution, and the solution satisfies the distance estimate, something like metric regularity. Yeah, if you are familiar with metric regularity, then this C is usually written on the right-hand side as 1 over c, and it is the constant in metric regularity. This statement is due to Graves when this reference point was simply x bar. And later, by S. and Donchev, was shown that you can make your reference point sufficiently close to the reference solution. So this is, I will call it the updated Graves theorem. And then the second statement is the Bartle-Graves theorem. And it again adds the continuity. So the Graves theorem says that the inverse mapping has a selection which is defined on a ball around the reference point and is calm at this point. And the Bartle-Graves theorem here adds something more. Then you can make your selection continuous. So again, it's a selection of the inverse mapping. It is calm at the reference point, and the added value is the continuity. Yeah. So this is the difference between Graves and Bartle-Graves theorem. Of course, you can find everything, all the details in the book by Donchev and Rockefeller. So you have here also the references, and the proof in the paper of Graves was always iterative. So some iteration either by points in the case of Graves theorem, or with a sequence of continuous functions within the proof of Bartle-Graves theorem. And you can everything find in the book by Donchev and Rockefeller, quite interesting, and also the generalization to set-valued mappings with convex pre-images. So now I would like to motivate this to show how the proof works, and then I will say it also for Bartle-Graves theorem. So I am starting with Graves theorem. So there is for each c, x, and r. So I fix it. I take some epsilon such that my c is still less than alpha minus this small epsilon, and I take some constant and another constant which is sufficiently small. So this is only technical, no general idea there. So the first general idea is here. If you have an open mapping A, then this means that for each point in Y, there is a solution of the linear equation, and again, metric regularity or openness with linear rate means that you can estimate the distance between 0 and h, which means the norm of the solution, by the norm of the right-hand side. So this is quite known, and no problem with that. So how to profit and to prove the Graves theorem? So I am proving the Graves theorem without the continuity. Okay, I have to take x, y, which are in these balls, such that again f of x does not equal to y. And so this inequality is strict, and I have to produce better point. So my v will be y minus f of x. So my y is, of course, non-zero. If you have x in the ball here, then you have also it around the reference point x bar, and also by 9 you find a solution H for this V such that you can estimate the norm of the solution by a constant times the norm of the right hand side. And the better point what I want to produce is this one, is this x hat, and it is produced in such a way that your x is given, and you simply add a multiple of the solution of the linear equation. This multiple is rather small. So if you compute the distance, then of course this is precisely this quantity, and I have some difference here, so I end up with this. And what I'm doing, I want to show that I can apply the error estimate, so the assumed error estimate. So if I compute this norm here, then here I use simply triangle inequality, and I plug everything inside, so this is from above. And then if you look carefully, then this is less than 1, which means that this is less than norm of V, and the norm of V is here up, and plus this quantity is less or equal than this one. And you have the reference point inside the ball, so you end up with this. If you cancel C on both sides, then you obtain that your reference point, the you knew better point, is precisely in the ball where you have the error estimate, which means that this quantity is less or equal than my constant mu times the norm of the difference between x hat and x, which is here, and I use it once more. So now the proof will be finished in the following way. I have to prove that my point is better. So I compute the distance between y and fx hat, and how can I do it? So this is simply triangle inequality, nothing else. If you look, here is f of x, here is minus, here is some guy, and it is equal to this guy by the definition and by the positive homogeneity of my linear operator. If you look what is my v, then this is precisely this is v. So you have v minus a small multiple of v. This is precisely 1 minus this multiple and norm of v, and then you simply switch what is inside the norm. You use this estimate here, so this guy is less or equal than this, and what you end up with is that you have something like this. Just remember that I have the following relation, that if I have lambda and I make minus mu, then I obtain alpha minus epsilon, because my lambda was this mu plus alpha minus epsilon. So this is just a technical thing that this equality holds. So you have equality here, and then of course my C was strictly less than alpha minus epsilon. So I end up with here and if I again multiply, then I have norm of V. Here I have gamma times C, and V is of course gamma V is greater than the norm of H times lambda, so you have this, and your V is precisely this guy, and this C is here, and this remaining thing what I have here is of course this norm. So if I want to recall and recap, I found a point such that this quantity is strictly less than the previous one minus C times the difference between this new point and the previous one. So now you can apply the proposition, and you simply conclude that the Graves theorem holds. So it is precisely this that x is such that f of x equals y, and I have calmness. So this is application of the first proposition I presented today. And what about the proof of the second formula? This is done very easily. You precisely repeat all the steps I have presented, just one difference. Instead of x in the proof, you take your phi at y, so you replace x everywhere by the value of my function which is given me in advance, and I want to produce my function f phi hat, and you simply replace everywhere x hat by the phi hat, which is defined in the similar way. Just one comment. I of course don't want to go inside the proof, although it is only 1 page and a half. Yeah, I will show you, but the replacement is this. What you have to do is of course to have this. So again, here you add phi of y, a multiple by a solution, but your new function has to be continuous. So here you don't, it is not suffice to use 9 because you have no continuity there. Of course, if you know Michael's selection theorem, you are lucky because you succeed. So just one small remark, that this mapping, which to my V, to my right hand side V, associates the solutions of the linear equations which has sufficiently small estimate on norm, then this mapping has non-empty values, closed values, convex values, and it's lower semi-continuous. Lower semi-continuous because the openness always means the lower semi-continuity of the inverse. So the proof again will be in the presentation, so just say 10 lines. And if you prove everything, then you can produce a selection of this mapping which is continuous. So you end up with a continuous mapping which to your V assigns the solution with the sufficiently small norm estimate, and you are done, because now you proceed exactly the same steps as in the proof of the Graves theorem. So you have your function phi satisfying some estimate. You want to construct new, better function, and how? Here is the idea of the proof. Now my V depends on Y in this way, and my new guy, new function, is continuous because this is continuous and this is continuous selection. So this new function is better than the previous one. I will scroll just the proof, yeah. So this is exactly as before, and this is the end. So one page or something, no iteration, and everything use just the criterion and the triangle inequality. Of course, Michael's selection theorem. Yeah? So this is my message and motivation. And I promised to give you some results. So let's go to the results which we proved with Marián. So first, we considered positively homogeneous approximations, and we had the two statements. Remember, the first one is the Graves theorem without the continuity, only calmness and non-emptiness of the inverse. So this is the statement which is for the first case of the Graves theorem. So you have a continuous mapping, you approximate it by a positively homogeneous mapping in general set valued, such that the following three conditions are satisfied. I will start with the first one. No, okay, I can start with any, but I will try to motivate it again. So suppose that you have a convex set of continuous linear operators, for example, of matrices from the Clark generalized Jacobian, then your H, X and H, will be simply nothing else but the script A, which means that the set applied to H, yeah? So it means that it is H, A at H, when A is from my set script A, yeah? So you can have this, and this mapping is obviously positively homogeneous. This second condition is the openness. Yeah, it's dual condition for openness, so it replaces this, that for each A in my script A, I have the image of the ball. Of course, here I have some additional constraints set, but simply it's this alpha plus mu times the ball in Y. So this condition, this second condition replaces the openness condition, and of course the third one is the approximation. Yeah, you have good approximation of your mapping. So you have this, and this is not enough. You have to assume something more. So you assume the following, that one of these conditions is satisfied, either A, B, or C. Just to comment it. For example, A. Your target space is reflexive, or the norm on Y is fresh as smooth. With the results in a renorming theory, you always know that if you have reflexive space, then you can renorm it in such a way that the new norm is fresh as smooth and arbitrarily close to the original one and is equivalent to this original norm. So essentially you can work in fresh as smooth Banach spaces, and the same is in the case B if y is separable, then you can renorm it in such a way that the new norm is equivalent, arbitrarily close to the original one, and this norm is Gatto smooth. And the last one is the assumption that you have weakly Hadamard smooth norm. So this is concerning the spaces, and you have also some assumptions on the values of H. So in A you have bounded values. Again, if H is given for a set A in such a way that my H of X, H, is this set, script set A times H, then you simply have this set bounded. Then this is enough to have boundedness here. In case of B, a relatively norm compact is transferred to my set script A. It's compact in SOT, strong operator topology. And in case of C, is compactness in what? In weak operator topology. Yeah, so this is A, this is B, and this is C to ensure that you have relative compactness, boundedness, and weak compactness of the values. And of course, the conclusion is that again your mapping is open with linear rate around the reference point. So once more, this is nothing about continuity, it's about the existence of the selection such that it is defined around the reference point and calm at this point. So it's generalization of the Graves theorem. And the last statement I want to present is the continuous version. So again, I add continuity to the statement. So the assumptions are a bit stronger, and I will show you the differences. So my mapping F is not only continuous, but uniformly continuous. For example, Lipschitz. Then, instead of the first condition where was positive homogeneity, then I assume more that I have something like this. If you are familiar with fans defined by Ioffe, then this is precisely the condition concerning the fans. And again, if your H of X at H is defined in such a way that you have something like this, the script A, so it's defined by the set of continuous linear operators, then this condition always holds. 2 and 3 are the same as before, so I don't want to comment it. And the last condition is new, and it's upper semi-continuity, which is in the first variable and is uniform with respect to the second one. Yeah, so this is upper semi-continuity, and if you work with something like Clark generalized Jacobian, then of course you know that this upper semi-continuity holds. And concerning the additional assumptions on the target space and boundedness, so again, your values have to be bounded. Again, the assumption concerning the set of operators is that it is bounded in the norm, supremum norm, and concerning the space, either your space is super reflexive or the norm on it is uniformly fresh smooth. Again, if I have super reflexive space, I can always renorm it in such a way that the new norm is equivalent, arbitrarily close to the original one, and uniformly fresh and smooth. So this is the key assumption, and you can replace this second assumption by a bit different one. So you assume relative norm compact values, and your space is either separable or uniformly Gaussian smooth norm. So again, if you have a separable space, you can renorm it in such a way that the new norm is equivalent, arbitrarily close to the original one, and uniformly Gaussian smooth. So I can simply write this statement and the previous one as well with the assumptions concerning the smoothness of the norm, and this is just to make it accessible to everyone. Probably not everyone is familiar with renorming theory and so on, so this is to do everything in one statement. And what is the conclusion? The conclusion, and I will end here, is that for each C, each reference point, and each R, you find a function which is continuous, has values in the constraint set, and is a selection of the inverse mapping, is calm, and once more, it is also continuous. So this is the thing we did with Marián, and of course, if you apply it in finite dimensions with Clark generalized Jacobian, you obtain the results which were recently published. So this is, I think that my time is over. I hope that I haven't destroyed everyone and spoiled the evening. Here is the morning, so it's perfect for me. And I would like to thank you a lot for the attention. And if you have any question, I will be happy to answer it. So thanks a lot.
Thank you very much, Radek. Very interesting presentation, also motivational. It's always good to see good mathematics presented here. And also the way you present it, it's not common, not that common at our seminar to write on the screen. And I was trying to learn something also from this point of view as well. Questions, please. I see plenty of experts in the audience, and I expect some of them to have questions. Please. I hear some sound in the background, but I don't hear any questions. If someone is asking, please unmute yourself. Okay, can you read the question in the chat from Alexei Izmailov?
I will stop the sharing, yeah, and probably I will see the chat then. Okay.
If you wish, I can read it for you.
Why you cannot spell out the names of the result? You mean this I will go. I probably have the reference here.
Alexei, so, do you mean the names of people?
Well,
you can just talk.
Radek mentioned at the beginning and at the end some recently published result, but without spelling out the names of the authors. There is some
problem. Okay, so I am sorry for this. Can you see now my screen?
Yes.
Yes, so I am speaking about the reference 2. So Arutyunov, Izmailov, Zhukovskiy, it's called Continuous Selections of Solutions for Local Lipschitz Equations. It has published in Journal of Optimization Theory and Applications, and it's quite recent, so 2020. Is this my answer?
In the finite dimensional case and for Lipschitzian functions,
Yes.
what you obtain, it reduces to the results from this work, right?
Yes, precisely. If I'm sorry that I haven't time to publish it, and also to mention it in the presentation, because the time was almost over, but of course I present it here. So the first statement is this one. It's a local statement, so the only difference is that we obtain some additional constraints at k, yeah, which is closed and convex, but essentially this is precisely the local result therein, and there are various results. The first type is local, which says that there exists a neighborhood but says nothing about the size of the neighborhood. Then the second result is concerning the semi-local case, which is this one, and again this is in the paper therein, and it is semi-local in sense that you simply say on how big ball your continuous selection is defined. So this is again a consequence of the results I presented today. And I want to emphasize that in the reference to the finite dimensional case, there is one more statement concerning the global version, and this statement is not covered with these two statements with Marián I presented, and we haven't tried it. I think that it is not a problem, but our paper is so long that we simply skipped the global version. So yeah.
The extension to the global version is also, you believe it is also possible, right?
Yes. Because just a small comment on this, if you take in the criterion from the very beginning, the case when you don't work with identity, then I believe that you obtain precisely the extension result. Yeah, so I have a selection and I have to extend it on a bigger ball, and this is the way how to prove the global result by this extension. And I strongly believe that this is the case, that it can be done.
Okay, thank you.
By the way, Alexei, you might consider also presenting at our seminar at some point. Probably already in 2021. Okay, do we have more questions?
I have one question which is a bit different.
Jonas, please.
Because I often have trouble to picture like what kind of scenario we would like to apply such results to. I mean, I understand that of course we want to have a better analysis and so on, and we want to explore like what kind of things we can do. But I always have trouble picturing what that really means. Is there some kind of standard example where we can see what this gives us?
I am not sure that I quite understand the question.
Yeah, you see, of course, I understand this is a theory about operators or about inverse functions, but where, in what kind of situation, in what kind of example, in what kind of application does this tell us something? And obviously, this comes from something. This Graves theorem, this was all developed for a reason. So my question is, I always get lost in the details. Like, what are we actually doing? What are we actually achieving?
The question is concerning the solvability of the equation, so the existence of the solution, the dependence on the changes in the right-hand sides. Yeah, so this is the motivation.
Yeah, but yeah, you develop.
And if you have a selection theorem, then you can probably do something in the case when you have, for example, ordinary differential equation where you have two types of variables. So one state variables which is appearing with the derivative there and the algebraic variable. And so one point is that you have differential equation with two types of variables, and these two types of variables is connected with some constraint, say algebraic constraint, for example, inequalities or something like this, and you want to find a solution of this coupled problem, for example, algebraic differential equations with index 1 and non-smooth constraint in the case of algebraic equation. So the way is to use the theorems, for example, for usual ordinary differential equation, but you need a selection of a solution mapping corresponding to the algebraic constraint, and of course the better properties you know that this selection has, the better for your solution you end up with. So you can then make some path following method and so on, but this is really vague claim. Yeah, so I'm sorry for that, but this is the motivation.
Yeah, so I can understand roughly where you would like to, in what kind of Banach space you would like to work and why and so on. Yeah. That's enough for me. Thank you very much.
For example, Asen Donchev and Vladimir Veliov use some of these results or this type of results in optimal control theory with big bang controls. Yeah, so.
It's a big topic. Plenty of people are involved and numerous applications, theoretical and numerical, plenty of applications.
And of course, the good theorem would be if the selection would be Lipschitz, not only continuous but Lipschitz. Yeah, but I'm sorry, I don't have any result in this.
But it's good to dream.
Yeah.
Do we have more questions, please?
One remark, if I can.
Someone is there, but I can't hear. Speak louder. Or...
Yeah, I'll just rearrange my microphone. Is that better?
Yes, that's much better. Yeah. David, please.
Just a remark, if you're interested in Lipschitz selections. So the world expert now is Pavel Schwarzman. And you can, I won't give you any particular papers. He has a long list you can find on Mathscinet or Archive.
Okay, thank you very much for your advice.
Okay. Good. More comments, suggestions? If not, thank you very much, Radek, for your really very nice presentation. Thank you, everybody, for coming, especially Europeans, for getting up that early to come to our seminar. And everybody, please volunteer to present at this seminar. We have a list of presentations for this year, but we haven't started the list for 2021. Send abstracts and topics, and please keep coming. Thank you very much. Our time is indeed over. And have a great day for Europeans, so have a great evening for Australians.
Okay, thank you very much.
Thank you, Radek. Thank you, everyone.
Thank you.
Bye.
Bye-bye.
Bye.
Thank you, Radek.
Thank you. I stop recording. Probably it will stop automatically.